There are many service providers, many telecommunications companies, and the lab, it's the real network because they don't have a lab. And the operations guys, when they're working in these environments, well, they don't get access to the lab. They're the operations team, right? The engineering guys, the design guys, they're the ones who actually get the real lab equipment. And if you do have a lab, there's usually a long line of people who'd like to get access to your lab. So this is a problem. You know, in many cases for these service providers, rolling out new services is not the problem, right? Designing new services is not the problem. The issue is how long it takes to get through certification, to get through testing, and then the last people who get access to the lab are the ones who write your bill. Those are the most important people because if you are a service provider, money. We like to send you a piece of paper and we like to take your paper back and that money we put in the bank. But they are the lowest, in many cases, the lowest on the list. So this is really a problem. You know, it's an equipment challenge. So let me give you the view from a service provider. So we ask you to operate a network. Yep, we ask you to roll out new services, new functions, or maybe just keep things ticking along as they were. So make new changes, but don't impact services. And do that every day. In many cases, many times every day. So we're going to do this. We're going to add new services. Oh, by the way, did I mention don't impact the services? So how do you know when you're rolling out your new service that you're not going to impact what's already in place today? Can you predict it? Are you sure? Do you trust what the engineering team gave you? It's 2 o'clock in the morning. That's when most people, or most of the service providers around the world, start to make changes. 2 o'clock in the morning is also the time when, if you have your little set-top box decoder, maybe at home, or your little broadband modem, they start doing firmware updates. You're not using it. Guess what? Your service provider is. They are now rolling out new changes of code or making changes in the network. Once upon a time, a service window would be something like midnight to maybe 6 a.m. These days, a typical service window is something like 2 a.m. to 6 a.m. So now I have to take 6 hours worth of work and crunch that down to 4 hours. And by the way, you don't have 4 hours because the way that these changes are planned is I have 3 hours in and 3 hours out, because if it goes wrong, I need to be able to roll everything back. So you used to have 3 hours in, 3 hours out. You don't. You have 2 hours in, 2 hours out. Can you do the same amount of work? Are you sure? Do you believe that the information that you've been given from your engineering team is accurate and they've tested it, that they didn't make a mistake? It happens all the time. It happens all the time. This is what happened on the 23rd of February, 2012. Can you see what's wrong? Nothing's wrong. No, is it? What was? Exactly. No, Australia. Australia disappeared off the internet. Did you know that Australia disappeared off the internet? No, nobody noticed, except if you were in Australia. Okay, Australia is not a very well-known center for content. If America disappeared off the internet, everybody would have known. Australia disappeared off the internet for about 45 minutes back on the 23rd of February. How do you quantify that? Well, I worked on the team looking at what happened there, and we actually spoke to the economics ministry. Back in 2012, the value of the internet economy to Australia was something in the region of 500 million Australian dollars. So if they were out for 45 minutes, let's call it the best part of maybe $8.5 million. When you have that happen, and okay, we're not talking about stock exchanges and banks where it's millions of dollars a second, but if you put it in those terms, suddenly people sit up and go, oh, this is not good. That was caused by a single operator error. Okay? Single operator error, and the whole country literally disappeared off the internet for 45 minutes. Swinburne University, it's in Australia. Again. Okay. Funnily enough, there's quite a lot of research that's going on down there around these kinds of things. Any of the people in this room familiar with BGP, the routing protocol? So some people are good. Okay, so BGP, the Border Gateway Protocol, is a protocol that runs the internet. What's really scary about this is it's completely independent. So if David's running a particular policy, he can create his own policy, and I have no idea about it. I only know what he sends to me. I don't know what he does inside of his network. No idea. And this is the way that the internet is built up. There is no central authority. There is no central view of what is happening in the internet at any point in time. You have thousands and thousands of independent systems and hundreds of operators all making mistakes all the time. Some examples of them. And this kind of stuff, I mean, that one at the bottom, that's what took down Australia. Okay? Guy made a perfectly innocuous change, and due to a whole series of other events, they managed to literally take Australia off the internet. Congratulations, you are infamous. What a great name for a service provider, Dodo. Okay, but these kinds of instances happen on a regular basis. Sometimes they are deliberate, okay? Sometimes maybe not. Sometimes they are just errors that take place. So what are these guys doing? So this is actually PhD research that we're helping with, is can you actually detect changes in the weather, changes in the internet that are happening, and can you determine whether is this a mistake or is it just normal? Coming back to all these discussions about, can you filter noise from signal? Can you actually detect these things, particularly since an incident like this ripples around the world? Some of you may remember about 6 years ago, YouTube, small little website, YouTube got taken down for about a day or so. Okay, some possibly targeted action coming out from Pakistan, where they started advertising prefixes, parts of the internet routing table from Pakistan, and everyone accepted it. Right? Everyone just, oh, okay, YouTube just moved. Everything went east. And all of this traffic started disappearing over there, and YouTube could do very, very little about it. It took coordinated effort actually to stop it, to filter it, and to bring this kind of stuff back. Shortly after 9/11, there were, I can't go into much of the detail about it, but there were some incidences that took place where governments started sitting up and paying attention. The internet is now national infrastructure. Okay, whereas it kind of was fairly loosely regulated, now you actually have governments looking at this. This is now along the lines of, and I'm sure you know, it's gas, it's water, it's electricity, it's internet access. Okay, it's in the similar vein right now. So some of the work that these guys are doing is trying to be able to look into that signal or look into the noise and try and determine what the signal is. But as we've discussed, I don't know how clear this is coming up, there's lots of different ways that you can look at this. We've got different kinds of sources of information that's coming through. So in the internet, you have these BGP updates. They're composed of something called AS paths and prefixes. So you can look at these things and you'll see changes in AS path that are happening. There's different approaches that can be applied, time series analysis, machine learning, a number of other statistical methods that can be provided to try and understand what's going on. Here's the problem. How do you model the internet? Thousands and thousands of separate systems. There are mathematical modeling tools. The problem is, funnily enough, the internet doesn't behave on mathematical models. It's commercial operating systems. So if you're familiar with NS2 and NS3, they're mathematical models. They use finite state machines, none of which exist in the internet. So how accurate are these models? There are test beds. Does starbed mean anything to people? No? Okay, so in Japan, they literally put together 500 plus computers, and if you're very lucky and you know somebody, you might be able to get a time slice on their platform to try and be able to do this. Okay, well, the guys at Swinburne don't have that, but they have this. Okay, so down in the lab, they have something like 250 routers and switches and lots of cables. Great, I want to reconfigure the testbed. No, you really don't want to reconfigure the testbed because, well, which one of the cables is it? They're all very nicely labeled. They're all yellow. Fantastic. Great. Does anybody know what this is? And why that data is important? No? Okay. Can you recognize the flag? Somebody might recognize a flag. Estonia. Yes, Estonia. That's correct. Estonia. So Estonian infrastructure got taken out for about 2 weeks around this time. Does that help clarify what this might be? No? Okay. Yes. Well done. You get coffee. Okay. So officially, this is the first incident of state-sponsored cyber warfare conducted against another country that could actually be attributed. Okay, there were other instances, you can look them up, but they're all kind of plausible deniability. This was open. Okay, this was open. This was the Russian government or whichever bureau it was that was conducting an operation against, in this case, the Estonian government. Please look it up. You can see what they were arguing over. It's all to do with the statue. Okay, but we'll come back to why this is important a little bit later. How do you model a network? We already said NS2, NS3, these are mathematical models. These are fine if you're looking at particular kinds of nature, but what you cannot model in this is humans, operator error, deliberate changes, inexplicable changes. The guy who comes along and unplugs something and then quickly puts the plug back in again. That stuff is much, much harder to deal with. How does this translate? Well, software developers today are busy writing applications. You're writing your application. You have your app for your phone or maybe some kind of distributed database. That's great. You build your environment. Maybe you test it. Maybe you don't. But if you're going to deploy this, then typically your operations guys want to know that this is going to stand up, that this isn't going to fall over. So you want to put this into some kind of stress conditions and try and make sure that the thing actually stands up. So if I'm a software developer, do I care about my test bed? No, I'm a software developer. I'm busy writing my software. You give me a test bed and, fine, I'll plug it in. So I need something which is relatively easy to configure. I don't really know about a network. The network guys do that stuff. I just write software. And I want to be able to use this. And by the way, I've got a team of other people who want the same thing as well. Remember what we said about the lab? I've got a lab. No, you can't use it. So this is a general problem. So we have come on with this idea that some of you may have come across, network controllers. Networks have historically been separate boxes. And yes, you may have network management systems that control all of these things. Now we're getting into orchestration systems, where instead of actually trying to control individual boxes, I'm going to try and orchestrate my network to perform some kind of policy, maybe prevent something, maybe you allow the students to have access to some part of the network, maybe not having access to the other part of the network. Well, here's the thing. What happens when the network starts misbehaving? What happens when my elements can't talk to my controller anymore? What happens when my controller is actually the target of attack? How does the thing hold up? These are really big questions. And again, how do you give somebody an environment where they can set it up, integrate it, do all of these things? And again, everybody's trying to do things in parallel, so everybody wants their own lab. Yeah, you can't have access to the lab. So then we now get into another area. Have people familiar with these terms Netops and DevOps? Yes, or it's very hip and trendy, and everybody can change the meaning to whatever it is they want to mean. But this idea that in software development you have continuous integration, people are patching in code, making changes, they're testing it, and as long as everything isn't broken, we're good, and we keep going, we keep going, we keep going. And if it is broken, we know who broke it. We can go back, fix it, and we carry on. Well, there is now moves to bring this kind of methodology into networks. With a lot of the tools that these guys are using for software development, for controlling servers in data centers now being applied into the network. Okay, if you go to Google, you go to Facebook, you go to Amazon, there's no guy running around configuring servers. Microsoft, no guys configuring servers. Everything is being done via software. Well, how do you know the software is right? And how do you know that your policy actually works? I need to be able to test. I need to be able to verify. I need to be able to ensure. And by the way, it's not one controller. It's not one application. It's many. And these things are all operating at the same time. So how do you make sure that the controllers aren't messing each other up? Because that can also happen. And of course, everybody wants their own. So we're back to this problem once more. Security is a very, very serious concern, particularly from internal attack. Some studies actually looking at where most security penetration events actually take place from actually come from inside the service provider. Typically, it's a subscriber already at home who's connected in. In many cases, it's a disgruntled employee, somebody who left something as a little back door and left, and then they are actually using that way to actually attack, to perform attacks. With more visibility, with high-profile attacks that have taken place, you know, PlayStation network getting compromised and everybody's credit cards going out, this is an increasing area. Security was very specialist, and there's still, you know, it's an extremely specialized area, but now it's starting to come down in terms of if you're going to put things out in the network, the security teams want to know that it is thoroughly tested, that it isn't obviously broken in some way with some open doors, and these things change. I'm sure you will have seen, oh, you know, there was something the other day where yet another vulnerability has been discovered. A lot of this stuff is latent, but more vulnerabilities. So they've got to adapt, they've got to react. It's a continuous process. So there are tools. These are just some of them. Kali is a very well-known one. Security Onion, another. Can these kinds of tools be brought into just a regular environment? So it's just happening. You know, you turn the handle, and all of this kind of stuff is just happening. For a lot of the guys who are doing development work, they build something. They build it on their laptop, maybe a little server somewhere. They put it on a server in the lab. And then when they actually start to deploy these things on scale, en masse, guess what happens? That. Because the way the systems behave in labs, unless your labs are very accurate, is not how they operate in the real life environment. If you go to AT&T or if you go to British Telecom, they have very, very large lab facilities, expansive lab facilities. British Telecom, any piece of equipment that is deployed in a live network, there is a copy of that in their lab environment. Guess what? You have no access to it. Okay? Only the guys who work in the lab get access, and if your operations teams, no, there's no lab. You know, we know how this game plays. So, you know, this kind of thing is a significant risk. So for a lot of the guys who are working on software development, this is their view of the network. It's magic. Stuff just happens. There is no latency. There is no jitter. Stuff is just, you know, it just works. Packets go down a wire. Packets come off the wire. Life is good. So is this realistic? No, it's not. But do they have a better environment that they can actually, you know, do these kinds of things? Things that happen in a network. Things that happen every day, every minute in the network, because the network itself is almost organic. There are changes happening at all sorts of different levels. Planned changes, unplanned changes. There was a fantastic case of a hospital when they were building the hospital, it's like, right, we have to be resilient. We have all this information. We need to make sure that our network connections are great. We will have 2 ducts into the building, one at the north, one at the south, and we will be diverse, and life will be wonderful. And they paid lots of money to have these ducts dug, and they went back to the exchange building, and they never realized that all of these fibers ended up in the same rack, one above each other. And when the power went out on the rack, that was that. These things happen, right? They are normal in a lot of people's, you know, it's just not what people normally think about. Yet we can bring these kinds of tools to developers. So similarly, when you can take these kinds of tools, put them on people's laptops, put them on servers so you can go at scale with exactly the same kinds of capabilities. I want to mimic that flaky link. I want to understand what happens to my data when some things going around in the back and changing routing and making all sorts of changes happen. How resilient is my application? Can we actually do this? So we can actually go to a point where software is tested in a more representative environment, not just this nice theoretical environment where there is no latency, there is no jitter. So, I want a lab. Can I have a lab? Can we create these kinds of things? The answer is yes, it can be done. And what we're doing is we're using virtualization technologies to do this. People familiar with virtualization? Yes, some people, a lot of people not. Okay, so you use Amazon or you use Google platforms, Google Engine or anything of that nature? Okay, you do not get a server in Amazon's environment. Okay, you don't. You are getting a virtual machine. Okay, and that virtual machine looks like a server. Great. Well, how about we go one step beyond that? What happens if we can actually create a network, virtual machines that behave like a network? Okay, so we're not talking about just servers that may run a web server or a Hadoop cluster or a Cassandra cluster, but actually virtual machines that behave like routers and switches, that have the same kinds of configuration capabilities as real routers and switches, that you can break in exactly the same way as real routers and switches. That's what we've been building. So I can literally go from something I've designed, a diagram. I want it to look like a network with various kinds of protocols that we have running around on the internet, configured the same way, and literally bring that environment up, a little bleached out. But what we're showing here is we can literally design our environment, stand it up as a set of virtual machines. Literally, I can run this on a laptop or up onto a larger server, log into these machines and operate them the same way as if I was that operator sitting there at 2 o'clock in the morning with not enough coffee and that change order that has the vital piece of information missing, and type the commands and see how the thing is actually going to react. How we've been able to do this is by taking the operating systems that run on the physical equipment. So if you go to Bezek, you go to Hot Telecom today, they have big switches, big routers. The operating system, we can take that and put that into a virtual machine. It's not the same, it doesn't have exactly the same operational behavior because we're not trying to mimic things like fabric, the fan trays, the ASICs. Okay, those kinds of things can be simulated, but they're incredibly intensive to do it. But we can take ranges of different virtual machines. You can even create your own. The technologies to create your own virtual machines or little containers, again, this is all out there and certainly available. And then be able to construct an environment. We're just using open source code to do this. So a particular project, something called OpenStack, to orchestrate our sets of virtual machines, to bring them up and merge them into, instead of individual virtual machines, a network of virtual machines that look and behave and react like a real network does. We also have, this is actually a PhD research project. One of the guys on my team has built this thing called Autonet Kit. The idea here is when you have a network of hundreds of machines, guess what? You've got to configure that. Well, you could do it one machine at a time, or we can use an automated configuration engine, which is what my team, Simon on my team, has actually built. So I can design a network, and without actually having to type any configuration, the configuration engine itself is able to create an appropriate configuration. Not perfect. It's not designed to guess exactly what you're doing, but all of the basic groundwork is being done for you so that when you bring these machines up, if I wanted to have a network of 100 machines, I have 100 machines ready to go, not run 100 machines and now having to sit there and type away. Managing networks of virtual machines is exactly the same complexity as managing hundreds of networks of physical machines. It's not simple stuff to do. Service providers spend a lot of time doing this kind of stuff. So we have a piece of glue in the middle. this thing, a service topology director. It allows us to take our diagrams, make a picture that looks like Bezek's network, HOTS network, whoever, AT&T, and literally translate that into a set of virtual machines and then bring all of that stuff up. So we go from an plane that's bleached out, diagrams, we process them, we create their configurations, we come back, we can review them, and when we're happy with it, we then actually spin everything up, and we end up with a set of virtual machines that are actually up and running, and then we're able to log in. So where do we go with this stuff? Well, as a result of that little incident in Estonia, NATO have their Cybersecurity Center of Excellence based there. They are training soldiers, and that's who they are in many cases, soldiers on cyber defense and cyber warfare. They run workshops literally every month, and they have large teams of people coming through. And funnily enough, most of those people who are working on these kinds of cyber defense and cyber warfare, they're not network experts. They are kids, 18, 19, 20, who are getting into this area. So how do you teach these frontline soldiers what is networking, what is cyber warfare? Can you do that on a regular basis? You can when you're starting to use virtual environments to do this. So at the CCD COE, they run warfare games. Literally every month they have teams coming in from across NATO and outside NATO, and they're putting these guys into environments where they have to play the red team, blue team, defend, attack, understand what actually happens. That lab down in Australia with their 250-odd routers, well, as I said, it's really difficult to reconfigure something like that. I want to mimic the internet. Well, the internet is not stable. It changes all the time. Right? New networks are being added on. There's an interesting game going on right now. You know about IPv4 address depletion? Some people do. Okay, so we're running out of internet addresses. It's the end of the world. Not quite. But there's an interesting market that's now appeared of effectively leasing IP addresses. So you have blocks of IP addresses that move around the internet. This week they're being used in South America. Next week they're being used in Indonesia. It brings a whole new series of problems. Are the guys in Indonesia allowed to use those addresses that are down in South America? Who knows? It's unregulated in many cases. So these things are changing, but these guys were able to collapse that lab into that. Okay, so for what these guys were looking to do, which is to modeling the control plane elements of the internet, they were able to go down from 250 physical devices and all those cables. And of course, the one you want is the one in the middle, and they're all yellow. Literally down to 3 servers and a switch. They're virtual machines. They can spin this up. They can reconfigure it. They can change it. It's so much easier for them to use. And the work, this is a PhD work that's going on right now. The guy who's, I think he's got about 6 months left on his PhD, but some really interesting work coming out from him. That diagram, which is rather bleached, is a very large service provider in America, Verizon. Okay. Large service providers have exactly the same kinds of problems. As we said, they have these labs. Lots of people want access to them. Not everybody can have access to them. In many cases, they don't need to have access to real equipment. Virtualized equipment can do a good enough job for them. So we did a project with Verizon where we literally modeled their core backbone. So it's 37 routers. They are using a particular protocol, something called MPLS-TE. We had the whole thing up and running, and it took about 2 days to do it. If you had to assemble that equipment and actually configure everything, you're talking about many, many weeks in some cases to actually pull all this kind of stuff together. They now have many of these because it was that simple to set this up. They can give this to the operations guys, the design guys, the field engineers. All sorts of different people can use it for training, for teaching, for looking at the what if, for learning how to break the network and fix the network. Because at 2 o'clock in the morning, it's these guys who've got to figure out what just went wrong and how do they actually get out of it. Okay, so just to leave you with some last thoughts. We did a paper back, SIGCOM ACM. Some people, maybe. Yes, okay. So we had a presentation at SIGCOM. This is back in Chicago. So there's a paper which goes into all of the work that's underlying this platform that we've built. This is now in a number of universities around the world. Swinburne is only one. We have about 20 others who are using this as a platform for research. It's not just a case of saying, hey, I want to be able to create a network, but it's a platform on top of which you can build a lot of interesting things. You know, build the next generation routing protocol and understand how it's going to work with their existing networks. You know, we're not going to be building a new internet from scratch, so everything's got to coexist. How does that actually happen? So if there are any people who are interested in taking a look at this, you know, please, we can talk afterwards. But some examples, and there's a lot of material there. You can take a look at some of the work that other people are doing. But this is also being used by individuals today. We have something like 10,500 users who are using this platform to learn, to understand what networking is. Students, consultants. One of my favorites is we came across a team who work underground. They work in the mining industry. There are ruggedized routers and switches down in these mines. Is there a lab 2 kilometers down? No, there is no lab 2 kilometers down. But they can take a ruggedized laptop and they can take it down with them and they can plug in and they can start mimicking and operating and working down at those depths. So again, you know, taking lessons that we've learned from data centers, virtualization, and applying that to networks, and now start bringing that to very, very practical uses, you know, 2 kilometers down in the mine, or whether it's training the next set of soldiers on cyber warfare and security, or bringing it to you guys for research. You know, what can we build with this kind of stuff? This is Lego. Do you want to build a plane, a spaceship? You tell me. Thank you.
Any questions for Joel?
Yes?
You mentioned to virtualize network.
Yes.
And you're doing it for lab, for simulation. But what about for doing the real networking instead of buying all those expensive Cisco routers? Just get virtualize.
So network functionality virtualization, NFV, is the term that is being used a lot today in terms of, can I take some, not all, can I take some of my very, very expensive routers and get rid of them and replace them with a computer running software? So yes, it's coming. It's there already today. For certain kinds of applications, absolutely. The issue is speeds and feeds. You know, when you're talking about terabyte links or 100 gig links, the computers don't keep up today. But if you're talking about specific functionality at the edges of networks, then absolutely, NFV is where it's going. And certainly if you look at most service providers today, they have either a view on where they want to go, or they're starting to do it already. So yes, absolutely. But there's another interesting issue that comes out from this. In the core of the network, you have maybe a few very large boxes. Today, because the NFV cannot do what those core boxes do, now I'm going to spread this way. I'm going to have many smaller devices. This is actually more of a problem for the service providers than this. More boxes to manage. So we haven't solved it. But yes, in theory and in principle and in practice, we're going towards that direction. But not for every device. We still need silicon to do what silicon is really good for. You know, software is catching up very fast. And we have machines now that are able to do 40 gig, in software. No ASICs, no special ASICs required at all. The Intel guys with DPDK and the next generations of DPDK, yes, it's perfectly possible. But that's 40 gig. That's not, 4 terabits a second on a single line card. So maybe some years. It's coming. Yes?
Well, I wanted to, say, I totally believe everything you're saying about the need to simulate these networks. And, someone that I know that a high executive at a major telco says that he thinks that's the only reason the internet works is that they have really faithful adherence to software development discipline. They test everything against labs and so on and so forth. Like
Of course they do, yes.
That's the only reason anything works. But as far as virtualization goes, it occurs to me that there must be some metric that shows that you're actually simulating what you purport to simulate. And
The fidelity question.
There wasn't anything in your talk
Yeah.
about that, and I just wonder if you could comment on
Sure.
the accuracy of the simulations you're achieving.
So the answer is, it depends. The reality is, if you really wanted to mimic, you need the same physical equipment. There is no replacement. One of the things about virtualization is time is not the same. Time in the physical world and time in the virtual world are not the same. We've even come across issues where the CPUs that are used in network equipment are typically quite low grade. You bring them to high-end computing equipment, and now stuff works faster because the class of the CPU is different. So you have to be very careful about what it is that you're modeling and the level of accuracy that you're trying to achieve. So today, we can and we do run exactly the same control plane software. So all of the routing protocols that we offer and operate in the internet, we have exactly the same, literally the same code. So that means the same undocumented features are present. And we can find them, right? We can find them. What it cannot do is that interaction between the physical and the virtual. So when we have a problem in the hardware systems, the software-only ones are very unlikely to be able to see it. So we're definitely not saying, you can get rid of all your physical lab equipment and replace it with virtual. No. But you can use it as an adjunct. And we can connect physical to virtual. So for many companies, labs are very expensive. And lovely if you have the money and the capability to do it. But the reality is they don't. And the lab is the live network. But if they could have, let's say 2 or 3 physical boxes, but surround them with virtual boxes, the physical boxes don't know that what they're talking to at the end of the wire is not real. They just see traffic. That, in many cases, may be good enough, or certainly better than, well, my lab is my live network. So to answer your question, it's never going to be exactly the same. From the physical perspective, there are ways of doing simulation in software. There is a suite, something that the ASIC designers use, something called CoSim. But for CoSim, it's designed to mimic the gates, to mimic the behavior of the ASIC. High speed for them is maybe 10 packets a second, because it's there really to make sure that this thing is valid and working before they go to do the most expensive thing. That's actually to build an ASIC. So could you use those kinds of simulators in this kind of environments? Not really. So it's definitely not perfect. And there are many companies who will say, I have physical equipment in my live environment, I have to have physical equipment here. But does everybody need physical equipment? In many cases, no. They can use, for certain tasks, right? They can use that virtual environment.
Do you advertise a metric that's supposed to convince potential customers that
The percentage accuracy?
that they can
That's an interesting one, yeah.
Like, how do you explain that you're successful to people?
That's a really good question. We haven't developed a metric, sort of like a fidelity metric. We should talk about how you could do that. It's very difficult to come up with a real level of accuracy because we're talking about physical equipments and some components which we do mimic and some components that we don't. For many people, what they're looking for is they want a clear understanding. What is the functionality that these virtual systems provide and what do they not provide? The simple way of looking at it is it's the same control plane, the same routing protocols that you're running, same code, the same management interfaces. All of that stuff is exactly the same. But if you're talking about anything which is hardware-based, no, that's not what these are for. So if you wanted to call it 60-40, maybe. But to actually hang a real hard metric on it, difficult. And then back to the point that the other gentleman was making, we have NFVs. Those are completely virtual software-based representations of devices. There is no physical device. So those machines, it's 100% accurate because it's the same software. So the answer is, David, it depends. but there's not a hard metric that you could hang on. But what I can say is that there are many people who are using this now constructively as a tool. It's a little bit of glass half empty or glass half full. There are things that virtualization does really, really well, and there are other things it's just not appropriate for. So can you find that sweet spot for your environment that these systems can really help you with? And in some cases, it may be they can't help you, but they can help colleagues. Right? It can help the operations guys. We did a project with one company, a very large social media company who shall remain nameless, where they did a complete migration of their operating environment, and they did it virtually 6 months before they actually did it in reality. And that process of actually going through 6 months in advance helped their operations team gain confidence, and they knew exactly what it was they were going to do step by step by step, long before they actually did it. So when they did the real thing, it's like they've already done it 10 times before. How do you measure? You measure that by nothing going wrong, maybe. So we prefer nothing going wrong.
If I understand correctly, one can actually buy, if it needs testing, enough of infrastructure as a service, and then to deploy over it any testing environment he wants, including network, hypervisor, and orchestrator, as he wishes. I want to understand the novelty of this testing, like doing testing as a service, which is sold to the customer as another service, or is it just providing some sort of environment of NFV, maybe structures as a testing?
So let me try and. So you're asking, is this a testing as a service,
yes,
or whether it's an environment?
Yeah. Is it a testing as a service?
No, it is not testing as a service. So it's a software package. Yes, you can use it for testing, absolutely. You could use it for testing. You can use it for development. You can use it for education. You can use it for training. It can be used for many different things. As I said, think of it like Lego. You can create all sorts of things. Question is, what do you want to use it for? Right? But the environment itself, as I said, we're using a lot of open source software there. But one of the key things that we bring is in proper in network provider environments today, you do not find people using open source routing protocols in production. Say they're out there. So things like Quagga, Bird, Zebra, very, very few people. There are a handful who would actually use these routing protocol stacks, open source, in a production environment. They use commercial. They'll use it whether it's from Cisco or Juniper or Alcatel or Huawei. They're commercial. They don't behave the same way. So if you're trying to replicate an environment for whatever purpose it is, using an open source routing protocol is fine as long as you understand that what you're doing is not mimicking your production environment, which may or may not be important. Yeah, it may or may not be important. But the fact that we can take commercial operating systems and bring them into an environment, virtualize them, now we have a great deal of flexibility and a cost. Well, a little Cisco router starts at, let's call it $1,000.
So it's a software that can scale?
Yes, hundreds of virtual machines onto these things. We're using OpenStack clustering to be able to scale at very large scale, and it's really then down to how much compute you throw at that problem. So we can go this way, we can go that way. Okay. Did that answer your question? Yeah? Okay. Thank you very much, and thank you for your attention.
We will come back at 4:35.